Okay, now that we've talked about pressure and we've got a good grasp of what that is and how we use it when we talk about gases, there's actually three other variables that we constantly use and talk about whenever we're talking about gases. So in addition to pressure, there is also the volume of a gas, its temperature, which we always report in Kelvin, which I'll mention why in a moment, and then just the quantity or amount in number of moles of the gas. And what we'll find is that there are multiple equations that relate these variables to each other, which we refer to as the gas laws. We'll go through a few of these, and then we'll see how they can kind of be combined together into one sort of uniform law to describe ideal gases. So before I move on, very quickly, just to mention, temperature always has to be reported in Kelvin because it must always be a positive value. It has to be the absolute temperature because if we had a negative temperature, as in using Fahrenheit or Celsius, then we could, in our equations, come out with a negative volume or a negative pressure or a negative number of moles. And those are nonsensical values. So we must have temperature always in absolute temperature in Kelvin. Okay, so let's go through a few of these gas laws and how we relate these variables. And this will take us back to a little bit of history. So back in the mid-1600s, there was an English scientist named Robert Boyle. He was studying gases and noticed a relationship between the pressure of a gas and its volume. It was a little bit interesting. What he noticed essentially is a phenomenon similar to this, where if you take a balloon and it has a certain volume, that as that balloon rises up through the atmosphere and the atmospheric pressure decreases, that the volume of the balloon increases. So essentially what he noticed is that there was an inverse relationship between pressure and volume. So the volume of a gas at constant quantity and temperature is inversely proportional to its pressure. This is the written out form of Boyle's law. Another way to sort of write this is that he noticed that the pressure of a gas times its volume was always a constant, which means that if the pressure increases, that the volume must decrease in order to maintain that constant, or if the pressure decreases, the volume has to increase to maintain that constant. Another way to write this is simply to say that pressure 1 times volume 1 is equal to pressure 2 times volume 2. So in the case of the balloon here, if we have a certain pressure and a certain volume to begin with, then as it rises up through the atmosphere and the pressure decreases, then the volume has to increase to maintain that constant. And so let's just go through a quick example of this, or what we can see here if we just plot. We can do a graphical representation of this as well, where if we plot volume versus 1 over p, we see a nice linear trend line between these. So there's a good relationship between those two, and it intercepts perfectly with 0. So let's go through an example of this. So if we had a fixed quantity of a certain gas at 21 degrees Celsius, and it has a pressure of 752 torr and a volume of 5.12 liters. If the temperature is held constant, calculate the volume the gas will occupy if the pressure is increased to 1.88 atmospheres. So we can use the equation that we have above. We've got, we can identify first off what we have. We have pressure 1, that's 752 torr. We have volume 1, that's 5.12 liters. We have pressure 2, that's 1.88 atmospheres, and we're asked to find volume 2. So it's a fairly simple problem. The thing we must pay attention to is simply making sure that our units match. So torr is one pressure unit, atmospheres is a different pressure unit. So we must make sure that those two units match each other. So we have to convert one or the other. So here's what we've been given and what we're looking for. We first start, in this case, I took the atmosphere unit, so pressure 2, and converted it to torr. and that's my pressure 2. So now my two pressure units are the same, and I can plug everything into the equation. I do a little bit of algebra to rearrange and solve for volume 2, plug those values in, and I'll come out with a volume of 2.69 liters. Now, I'll notice that if I compare my pressure 2 in torr to my pressure 1 in torr, my pressure 2 is significantly greater, so my pressure has increased. So therefore, my volume must decrease. So I started out at 5.12, and now I'm only at 2.69. So that's the relationship between pressure and volume. Then what about the relationship between temperature and volume? So again, a little bit of history. Now we cross over the channel. Jacques Charles is a French scientist, and in the 1700s, he was studying gases as well and looks at the relationship between temperature and volume. Essentially notice that if you increase the temperature, volume increases. If you decrease the temperature, volume decreases. So written out, what that essentially means is that the volume of a gas, providing that the quantity and the pressure are held constant, is directly proportional to its temperature. Since those are directly proportional, then we can write that the volume over the temperature is equal to a constant. If the volume increases, the temperature must also increase to maintain that constant. If the volume decreases, the temperature must also decrease to maintain that constant. And we can write, similar to Boyle's law, we can write this as V1 over T1 is equal to V2 over T2. And we can plot volume versus temperature and see that there's, again, a very nice relationship here between volume and temperature that nicely intersects with negative 273 degrees Celsius, which would be 0 Kelvin. And we notice that at absolute zero, that we would have 0 volume for our gas. At very absolute zero, that all of our molecules would have come so close together, we'd essentially have 0 volume. So let's do an example of this then. So similar case, we've got a fixed quantity of a gas, some gas X at 21 degrees Celsius. It's got that pressure of 752 torr and occupies the volume of 5.12 liters. Same case. In this case, we held the pressure constant, and we want to know what's the volume if we increase the temperature to 175 degrees Celsius. We've done a significant temperature change. So what we're looking at here is we've got temperature, we've got T1, we've got V1, we've got T2, and we're looking for V2 again. The important thing to note here, though, is that our temperature values are not in absolute units. They are currently in Celsius. They must be in Kelvin. We cannot do these calculations unless we convert them to Kelvin first. And so we add 273.15 to both of these, and we come out with 294 Kelvin for T1 and 448 Kelvin for T2. Now we can substitute those into our equation, do some algebra to rearrange and solve for V2, and we come out with a volume of 7.80 liters. So our temperature increased, and so our volume increased as well. Lastly, let's go through one more law. This is known as Avogadro's law, and it's named after Amedeo Avogadro, who was a scientist in the early 1800s. And again, studying gases, he sees this relationship between quantity, so the amount of a gas and its volume. And what he noticed is, in terms of moles, that it did not matter what the identity of the gas was, as long as the quantity in terms of number of moles, as long as the number of gas molecules was the same, the volume is the same. So as long as the number of gas molecules is the same, then the individual identity of those gas molecules doesn't matter. the volume will be the same. So there's this relationship here where the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of a gas. And this is probably the most intuitive. So if we increase the number of moles, or the quantity of the gas, that the volume of the gas will increase. The thing to really point out, though, is that it's dependent on the number of gas molecules and thus on the number of moles of gas, not on the mass. So in these cases, in this example, we've got helium. There's only 4 grams of helium will occupy the same amount of space as 28 grams of nitrogen. And that's because the number of molecules is the same between those two, but the masses are different because the molar mass for those two species is different. We can write this graphically here, or mathematically, as just volume over N, where N is a symbol that we give for number of moles is equal to a constant. And we can write this equation as just V1 over N1 is equal to V2 over N2.